Hi everyone, welcome back to the session 2 of our ML algorithm series. In this particularly, we are discussing the theoretical and practical implementation of various machine learning algorithms from scratch. So in our previous session, we discussed about linear regression. In this session, we are going to discuss about logistic regression. Coming on to logistic regression, basically it's a statistical method used for binary classification. One of the very important questions that people try to trick you in logistic regression is if logistic regression is regression in its name, then is it a classification or regression method? And please remember that it is a classification method. This logistic regression is particularly used to predict the probability of event occurring or not. It is a type of generalized linear regression that is used when dependent variable is either binary or categorical. And in this particularly the y that we have, the output that we have, that is binary, and the independent variables can be continuous or categorical. It depends. And the goal of logistic regression, like linear regression, is to find the relationship between different independent variables and a dependent variable, but by estimating the probability of dependent variable being 1 given the values of independent variable. So the logistic regression model uses a logistic function, which most of the people know by the name sigmoid function, to map the input values of the independent variable to a value between 0 and 1, which finally represents a probability of the dependent variable being 1. The logistic regression is generally defined as p equals to 1 plus e raised to power minus z, where p is the predictive probability of the dependent variable being 1. E is the exponential function. And the logistic regression model estimates the value of coefficients of the independent variables that maximize the likelihood of observing the data given the model. So generally in this, we use maximum likelihood estimation or gradient descent optimization. And similar to once the model is trained, you can use it to make predictions. So before coming to the coding part of this thing, maybe I'll try to explain you what was written here in the above formula. So it mentions, like, if you can see through the figure, what was happening in the linear regression model, y equals to b beta naught plus beta 1x. However, in logistic regression model, we are saying the probability of it being 1 is probability equals to 1 upon 1 plus exponential raised to power minus beta naught plus beta 1x. So the earlier linear term that we have is like what we have inside of this exponential function. So I think, like, keep this particular thing in mind, and it will be very useful when we go over through the code. So in this particularly, if we go through the code, so what we are doing here is we are importing NumPy, then we are creating a logistic regression class in which we are defining a learning rate, number of iterations, weights and biases as initialization of that. Then we are defining a fit function in which we are defining, like, how many samples, number of features that we have. Then for weights, we are initializing them with 0 values, and biases we are also defining with the 0 values. Now we are writing the code for the gradient descent optimization in which we are seeing, like, for all the number of iterations that we have in each iteration, do they calculate z. Z is nothing but x into weights plus self dot bias. So z is nothing but the value that we were getting here, p naught plus beta 1x. Z, we are calculating this thing. And in the next line, what we are saying is y equals to sigmoid of z. I hope you are already aware this function is also known as sigmoid, 1 upon 1 plus e raised to the power minus of z. That thing is known as sigmoid, and z here is beta naught plus beta 1x. So then moving forward, uh, in the um, in the in this particularly in the logistic regression, the cost function is defined in such a way. So I'll maybe try to have it through. Yeah. So in this particularly, the cost we are defining, the j is we are defining it is 1 upon m summation of cost of h theta comma y, where cost of h theta comma y we are saying is equal to minus y log of h theta x minus 1 minus y log of 1 minus h theta x. And in this, if we are applying the gradient while we are doing gradient descent, what we will be saying, like, theta nu equals to theta old minus alpha times the cost, the j that we have, the cost function that we have. So this thing alpha time this j theta. So now coming back to the code, what I am doing here is minus 1 upon m, what was the number of samples, into summation of y into log of y prediction, 1 minus y into log of 1 minus y prediction. And then in the next step, we are trying to calculate the gradients in both the w and the beta. So in w, what we are saying is 1 upon n into np dot x transpose into y prediction minus y. In this for beta, when we are calculating gradient, what for gradient, if you want to find like just try to differentiate these terms with respect to partial differentiate with respect to m with respect to the slope and the intercept that we have, and you'll get these values. So if you do for beta, you'll find the gradient in such a way. For the further calculations, we won't go into much details, but if you are not clear, please go back and see the please go back and try to do these calculations manually. And then finally, once we got dw and d beta, what we are trying to do is like weights equals to the earlier weight that we have minus learning rate into dw that we got. Similarly for bias, what we are saying, bias equals to initial bias minus learning rate into d of bias that we got. And finally for prediction, what we got like after all these computations, we already got the w weights and the biases. So now what we are saying is z equals to x dot w plus bias. And then finally y prediction equals to sigmoid of z. And then we are returning the yz in the integers like for because we are saying the finally we are telling whether this thing belongs to one class or the either zero or either one, like converting probabilities into two binary predictions. And then finally in defining sigmoid z, what we are saying is in this particularly for sigmoid here when we had, so here we are using sigmoid, defining sigmoid here, that is, and I think we are using underscore here because generally sigmoid is a standard function that's defined as part of Python, and so that if we do not mess around with the already existing functions, we are trying to use underscore. Yeah. So for testing this thing, what we are trying to do is like for the data sets that we for the data set that we have for the first entry 1, 2, the final value is 0, and then for these the final value is 0, and similarly for these the final values are these respectively. Then we are initializing the logistic regression class that we have and making a instance of that class lr, and then lr we are fitting on x and y, and then finally we are getting a new x where we are saying like these are the new inputs that we have, and try to tell what's the y prediction for this thing, and for both of these value it predicts that these things belong to the class 1 and 1. So there can be certain improvements in the code, just what we have written. So the improvement can be like to this particular function is like very prone to overfitting based on number of iterations that we give, and to prevent it from overfitting, we can add the regularization parameter. Second thing is instead of gradient descent, what happens is sometimes if we are doing gradient descent for millions of entries, it's very hard for it sometimes becomes very hard for us to fit millions of entries into the memory of the machine that we are using, and it might sometimes go out of bounds. So for that, like to make it less computational heavy, what we do is we use stochastic gradient descent or mini batch stochastic gradient descent. I think like the video, if I try to explain these things and the implementation of these in this particular session, it might get too big. So I'll end this session here and continue the next session from here only. Thank you very much.